let's get the area of the circle in a different way. Suppose we have our circle again right here. So I have this and I need this and I don't need this. So here I have my circle again and I want to get the area of this circle. I know that the area is equal to the integration of 1 multiplied by dA. In the previous video, I chose dA to be a small rectangle in the Cartesian coordinates. In this video, I'll choose two different representations for my area. So the first representation will be a very small circular area. So something like that. So I have one circle and another very close circle to this circle. So maybe something like this. And I am choosing this width to be very small. So this is some kind of a ring. So this is my new area and we have multiple rings at different radii from the origin, and I want to add up all of those areas for all the different values of r. So in this case, I choose that my area is not equal to dx dy, but my area is equal to the area of this ring, and the area of this ring is equal to the length of this circle, which is 2 by r, which is the peripheral of a circle, multiplied by this very tiny amount that I will call dr. So this is a very small amount. So 2 by r dr. Now I want to add all of those areas until I finish the complete circle. So I need to integrate over r from r equal to 0 up to r is equal to capital R. So r equal to 0 to capital R of 2 by r dr. Now this is equal to 2 by, the integration of r is r squared over 2, so r squared over 2, and I will substitute from 0 to r, and this will give me by r squared. And that's it. Using a more convenient representation for my very small area, dA made my integration much simpler. But that wasn't a double integration, was it? Well, we can still make this a double integration by choosing a different representation of our dA. So I can choose my dA to be some area around this curve. So something like that, and like that. So this can be my dA. Now this dA is equal to the length of this curve multiplying by this very small amount again. So this is my new dA. Now the length of this curve is equal to the radius here, this radius, multiplied by this angle. But this angle right here could be chosen or should be chosen to be very small, so it will be equal to d theta. So this very small area is really equal to, dA is equal to r multiplied by d theta to get this length, so r d theta, and then I multiply by this thickness, which is equal to dr. So my d area is equal to r d theta dr, and I want to integrate in both directions. I want to integrate over this whole ring first, so from theta is equal to 0 up to theta is equal to 2 by, so I will generate this ring and then I will integrate this ring or add all the rings from r equal to 0 up to r equal to capital R. So I want to integrate my dA, which turned out to be equal to r d theta dr. Here theta changes from 0 up to 2 by, then r changes from 0 to capital R. Now integrating with respect to theta, I will get this equal to from 0 to r theta multiplied by r here, and I will evaluate theta at from 0 to 2 pi, and here I have dr. Now this will give me 2 pi, so I will have the integration from 0 to r of 2 by r dr, and this is again equal to by r squared. Very well, so we have seen how the change of variables made our integration much simpler, but in this video, our change of variables was kind of intuitive. I just chose a different dA. I completely knew from geometry what I should be doing. But that's not enough in all situations. Sometimes the situation is much more complex that I need a more analytical solution to do my change of variables. For example, I might want to evaluate the integral of something dx dy, but I want to do some variable substitution such that u is equal to, let's say, x squared plus e to the power of y, and v is equal to, let's say, x plus y squared, for example, and I want to know how could I change my integral right here to produce the correct result without resorting to geometry too much. Of course, this also will be helpful if I want to integrate some function f of x and y over this area dA. We'll start talking about that in the next video.